Hello friends, welcome to the video lecture series on digital image processing. I am Dr. Dafda, and in this 70th video class of DIP, we will study boundary descriptors in image description for digital image processing and its implementation in MATLAB. We are learning image representation and description and image representation techniques we have already learned in our previous few video classes. Now we will learn description or descriptors in image representation and description. Starting with the name, what is the meaning of boundary descriptor? As the name suggests, boundary descriptor is one that describes the boundary. That is how the boundary is. For example, what is its length, curvature, etc. Okay. Also, they allow us to calculate the property of any object, and it can be used to do a comparison between two different boundaries to find whether the boundaries are same or different. Okay, so let us start. These are the main steps of image processing, from which currently we are learning image representation and description, and after image representation now we are learning image description techniques. And as we discussed in the starting of this chapter, image representation and description comes under high level image processing. So image representation was converting an image into suitable format for processing, while image description refers to extracting meaningful information from the image for various tasks such as object recognition, classification or retrieval. So in image description, we will be extracting some useful or meaningful information from the image. For example, what is the shape of the object, what is the length, diameter, area, etc. Image descriptors can be broadly of two types: boundary descriptors and regional descriptors. Boundary descriptors are one that comprises of boundaries, for example, boundary length, boundary diameter, boundary curvature, etc. And regional descriptors are one that comprises of regions, for example, what is the area of the object, compactness, etc. Now these boundary descriptors are of three different types: simple descriptors, for example, length and curvature; shape numbers are one that gives the first difference of smallest magnitude; and Fourier descriptors that uses discrete Fourier transform for the description process. In this video lecture, we will learn different boundary descriptors. Okay, let's go ahead. First, we will understand simple boundary descriptors. So the first simple boundary descriptor is the length, which can also be called the perimeter. The number of pixels along a boundary gives its length, and for a chain coded curve with unit spacing in both the directions, the number of vertical and horizontal components plus √2 times the number of diagonal components gives its exact length. So say this is the boundary for which we want to find out the length. So say this is unit spacing, that is the value is 1. So for a chain coded curve with unit spacing in both the directions, the number of vertical and horizontal components and √2 times the diagonal component. So this is a diagonal component, so it will be √2, gives its exact length. So this will be the length of the boundary. Next is diameter. If you want to calculate the diameter of an object, we have to calculate the distance between 2 points, say Pi and Pj, and the maximum distance that we find out between Pi and Pj will be the diameter. And this distance d we can measure using either Euclidean distance, city block distance or chessboard distance, which we have already learned in video lecture number 5, neighborhood, adjacency and distance measures. So here these two extreme or distant points that will give the maximum value of d will be this point and this point. So as we can see, this diameter is also the major axis of this shape. Next simple boundary descriptor is major axis, which we have just seen. Major axis is the line segment joining the two extreme points that comprise the diameter. So here two extreme points are A and B, and this is the diameter. Next is minor axis. What is minor axis? Minor axis is the line perpendicular to the major axis, and two extreme points on the minor axis and two extreme points on the major axis should be the 4 points on a box that enclose the boundary completely. So this is the major axis, and the line perpendicular to this major axis having two extreme points is this one. So this box will enclose this boundary completely. So this will be the minor axis. Okay. Next is eccentricity. The ratio of major axis to the minor axis is called the eccentricity. So E is equal to major axis D upon minor axis M. Okay. Next is curvature. Curvature is defined as the rate of change of slope. Curvature at the point of intersection is defined as the difference between slopes of adjacent boundary segments. So here there are two boundary segments, this one, and this is our vertex point P. To calculate the curvature, the boundary is traversed in the clockwise direction and P belongs to a convex segment if the change in slope at P is non-negative, that is positive, otherwise P is said to belong to a concave segment. So this is our x-axis, this is y-axis. For this segment, the slope is say theta 1, and for this segment, the slope is say theta 2. Then the difference d is equal to theta 2 minus theta 1. So if d is equal to positive, that is theta 2 is larger than theta 1, P belongs to a convex segment, and if d is equal to negative, that is theta 2 is less than theta 1, then P is said to belong to a concave segment. Next type of boundary descriptor is the shape number. The shape number is defined as the first difference or the difference code of smallest magnitude, and by code we refer here to the chain code, which we have already studied in our video lecture number 65. Order n of a shape number is the number of digits in the representation, and n is even for a closed boundary. Say for example, this is a closed boundary and this is for order 4. This is the starting point, and we know from the video lecture of our chain code that for writing the chain code we travel in the clockwise direction like this, but of course the chain codes are defined themselves in the counterclockwise direction like this. First we are traveling towards the right, the chain code is 0, so here it is written 0. Then we are going down, so down is 3, so we will write here 3. Then we are going left side is 2, so we will write here 2. And then we are going up, and going up is 1, so we will write here 1. So the chain code is 0, 3, 2, 1. And also for calculating the difference code, we will be traveling in the anti-clockwise or counterclockwise direction. The first number is written by taking the difference between the last number and the first number, that is going from 1 to 0. So here it is 1 and we have to go to 0. So how many differences we have to take, or how many steps we have to cross? First step 1 to 2, second step 2 to 3, and third step 3 to 0. So total 3 steps are to be traveled to reach to 0. So the difference will be 3. Next we have to go from 0 to 3. So this is 0 and we have to go to 3. Again we have to travel 3 steps, 0 to 1, 1 to 2 and 2 to 3. So again the difference code will be 3. Next we have to go from 3 to 2. So this is 3 and we have to go to 2. Again we have to travel 3 times. So this also will be 3. And last we have to go from 2 to 1. So this is 2 and we have to go counterclockwise up to 1. So again we have to take 3. So the difference again is 3. So this difference code is obtained by calculating the directional changes that are required to go from one point to another point. And remember, we have to also take care that the difference code should be of smallest magnitude. So to make this difference code of the smallest magnitude, one way, as we have learned in the video lecture of chain code, is to bring zeros ahead. But here, as there are no zeros, we will keep the difference code as it is, and that is our shape number. So now we can see that in the shape number there are 4 digits, 1, 2, 3 and 4. So order n, that is order 4, is the number of digits in the representation. Here there are 4 digits and n is even for a closed boundary. So this is a closed boundary and n which we have received is also a even number. So this is how we find the shape number. Let us calculate the shape number for this. This is our starting point. First we are going towards right and again we are going towards right. So that means 2 zeros. Then we are going 1 down. So down is 3. So 3. Then 2 left. So 2, 2 and 1 up is 1. So first difference is calculated by taking the difference between the last digit and the first digit. That is 1 and 0. So how many directional changes are required while going from 1 to 0? 1, 2 and 3. So first will be 3. Next going from 0 to 0. 0 to 0, no directional changes are required, so we will write 0 as it is. Next going from 0 to 3, so from 0 to 3, 1, 2 and 3, so we will write 3. Next going from 3 to 2, so from 3 to 2 again 1, 2 and 3, so again we will write 3. Next going from 2 to 2, so 2 to 2 will be 0, and last going from 2 to 1, so 2 to 1, 1, 2 and 3, 3 directional changes are required. So now to make this difference of smallest magnitude, we can bring ahead this 0. Okay, so when we start writing the digit from this 0, we will write 0, 3, 3, 0, 3, 0, 3, 3, 0, 3 and this 3 will come at the end. Okay, because we will consider this as a circular sequence. So our shape number will be equal to 0, 3, 3, 0, 3, 3. Digits are 6 and 6 is also even number. Similarly, we can find the shape number for this order 8. I hope it is clear. The next type of boundary descriptor is the Fourier descriptor. The Fourier descriptor represent the boundary as a sequence of coordinates and they convert the object's boundary into a set of numbers in the frequency domain capturing its essential shape features. And we know that if we convert it to the frequency domain, we can remove some of the components such as high frequency components and make our description process simpler and more efficient. Fourier descriptor treat each coordinate pair as a complex number. Consider a Cartesian plane like this, where x-axis is the horizontal axis, the y-axis is along the vertical direction. So now in this digital boundary there are several coordinates such as x0, x1 up to xk minus 1. Similarly, y0, y1 up to yk minus 1. So the last value will be xk minus 1, yk minus 1. That is, we have in total capital K points. As usual, we are traversing the boundary in the clockwise direction, and we can also write sk like this. Sk is equal to xk plus I yk. That is, we are writing our x coordinate as the real value and y coordinate as the imaginary value, and we are forming a complex number. So by doing this, what we have done, we have converted this two-dimensional parameter into a one-dimensional parameter. And now we will find the discrete Fourier transform of this sk, which will be in one-dimensional representation. And we know that the DFT is given by this equation. As this sk ranges from 0 to k minus 1, similarly this u will also range from 0 to k minus 1. So from the DFT of the complex number, we get the Fourier descriptors, that is the complex coefficients a of u. And obviously, taking the inverse discrete Fourier transform of a of u will restore the values of sk. Now suppose that rather than using all the coefficients of a of u, we use only the first p Fourier coefficients of a of u. That is, the value of a of u is set to 0 if u is greater than p minus 1. That is, we are only considering the first p values and setting all the other values to 0. So now the new sk that will be restored will be given by s cap of k. Here k will be equal to 0 to k minus 1 and u will be equal to 0 to p minus 1. So actually what we are doing here, we are removing the high frequency components of signal a of u. By removing the high frequency components of a of u, we will be removing some minute details, but the overall structure of the boundary will be preserved. This figure shows a human chromosome which contains 2868 points, and these are the boundaries reconstructed using 1434, 286, 144, 72, 36, 18 and 8 Fourier descriptors respectively. And this last figure is just 0.28% of the original figure. So hence we can see that as we remove more and more coefficients, more precision of the boundary is lost. So these three figures looks like chromosomes, but very minute details are lost, and the last figure doesn't even look like a chromosome, right? In this way, we can use a Fourier descriptor as the boundary descriptor and simplify the description process and make it more efficient. Okay, let us implement some simple boundary descriptors in MATLAB. So that is all for this video class. Thank you very much.